Hello, and welcome again to a new lecture in Cantera. Today, we will continue from the discussions that we left off in the previous video. And we will learn a little more about fuel-air mixtures. But before proceeding towards Cantera and its scripting, there is one small concept that we need to revise. I'm pretty sure all of you know about it, and we'll just review it very quickly. That's the equivalence ratio. The equivalence ratio is the ratio of fuel to air that is present in a mixture divided by the fuel to air ratio that should be present if stoichiometric combustion is taking place, which is to say that if all of the oxygen available has to be used up by the fuel, that is known as stoichiometric combustion. And if there is any excess oxygen or less oxygen, or which in turn also means excess of air or less of air, then the equivalence ratio changes from 1. So if the equivalence ratio is greater than 1, that means it is a fuel-rich mixture. So there is more fuel as compared to the stoichiometric conditions. And if the equivalence ratio is less than 1, then that means it is a fuel-lean mixture, which is to say that the fuel is less than it should be if stoichiometric combustion was going on. And so that is a lean condition. So with that brief knowledge, now let's go and jump into Cantera. So I've again, well, this is all from the previous lectures. Let me just clear it out. And I will reset the reset spider here. So if you write percentage reset enter, what happens is if I hit Y and enter, then all the variables that were formed from the previous runs and scripts are erased from Cantera's from Spider's memory. So that is what we've done. So we are starting fresh. I have here a small script again. This the purpose of this script is to form a combustible mixture of fuel and air. In this case, again, the fuel is methane, and instead of air, I've only taken oxygen, so that we can understand a couple of concepts, and also it'll make things easier as you'll see. And so we are trying to produce a mixture at a prescribed equivalence ratio here. And we'll, again, as always, we'll go line by line through this entire code, and I will also execute every line individually in the console. Additionally, I mean, if you want to run this entire script all at once, you just have to press the play button. But for more clarity, I will go line by line. So for equivalence ratio, you see this command here, that is a new one. All of these have already been covered in the previous lecture, but this gas.set equivalence ratio is a new one. Let's see what this does. So again, you can just type help, and as you can see, gas is an object of the solutions class. And let's first start with just the basic help on the solutions object. Right. Oh, again, sorry. So Cantera, since we erased the memory from Spider, it does not know what Cantera is, what CT is, what solutions is, what gas is. So let's run this line by line again. So I'll just copy and paste this line in the console with an enter. Now Cantera has been imported. Let's go and produce an object called gas of solution class. Now let's go and type in help. Okay. And if you keep scrolling, someplace you will find set equivalence ratio function with some description in there. Let's see. Should be here somewhere in this long list of items. Just have to be patient. There is another way, easier. Oh, here it is. There's another way where we can straight away look at the help for equivalence ratio function, but I'll show that too. So this here is the set equivalence ratio function, and again, this is a part of the solutions class. If you directly want, if you don't want to scroll and look for all of these minor details in this long list, what we can also do is type help. So help, okay, gas dot the name of the function, which is set equivalence ratio. Is that it? Yep. All right. So if you write help in brackets, the object name and then the function name, it straight away jumps to that part of the help code, which gives you the exact definition for that particular attribute. So it says for set equivalence ratio, you need to provide the equivalence ratio. Fire here is the equivalence ratio, the fuel, and the oxidizer, and that's it. So for an example, they say gas dot set equivalence ratio 0.5 CH4 O2 N2. So 0.5 here is the equivalence ratio. CH4, you see, it has been mentioned in inverted commas and in quotes, sorry, and so that means this is the fuel consists of 100% methane, whereas here if you see oxygen as well as nitrogen both are within quotes, which means that the oxidizer comprises of 1:3.76 ratio of oxygen to nitrogen. And that is exactly what we've done here as well. But we'll go line by line, as I've already mentioned. One small thing that I forgot to mention in the previous video was these grayed out lines, which have this pound sign in the beginning. So as soon as you put this pound sign here and start typing anything, that entire line becomes a comment. So the Python interpreter will just ignore it. It will act as a comment, which obviously you can use for your benefit in understanding in the code and writing more details about the code inside the text. But the Python interpreter will just ignore it completely. All right, so let's do something. Let's form a mixture. Or let's see. Okay, so as if we go line by line, this you obviously know. I mean, that's we just importing Cantera. This here we are finally we've made an object called gas. Here we are assigning the state to this object or to the phase in terms of temperature, pressure, and mole fraction. So that we say that this particular phase of gas has a temperature of 300, a pressure of 1 atmosphere, CT.1 _ ATM. This is also, I mean, you can set the pressure of 1 atmosphere in this way as well. The other way obviously is to type it out 101325. But if you don't want to do that, Cantera already has this inside its memory. So you can use this term and assign 1 atmospheric pressure to any mixture. And then finally, for the mole fractions, what I've said is just assign 100% nitrogen to this entire mixture. There's nothing else except 100% mole fraction of nitrogen. So here we've assigned the, we've initialized the gas. And then we go on to mention that let's set the equivalence ratio at 1. So let's see what happens if we have an equivalence ratio of 1. And then finally, in this last line, this gas.set equivalence ratio, as we've just seen, we are just setting an equivalence ratio of 1 for a fuel and air mixture, which comprises of 100% methane as fuel and 100% oxygen as oxidizer. So if we run the code now, let's do that. So we just hit the run button. Okay, it runs, and now let's see what has happened. Okay, so you see the temperature is 300, the pressure is equal to 1 atmosphere. Then there's a certain amount of density as per the ideal gas law. Here, if you see, something interesting has happened. You have a certain amount of methane and then certain amount of oxygen, and you can look at the mass fractions and the mole fractions here. And you can also do that using the mole fraction dictionary, as we did previously in the last lecture. Let's quickly do that as well, just to refresh. Mole fraction. All right. So you see, for mole fractions, we have 33% methane and 66% oxygen. Now, if you look at the stoichiometric equation for methane combustion, you will see something similar. So let me find, maybe we can, either I can Google it, or we can also write one on our own. Let me try and Google that. All right. Now, again, this was a very simple equation. We could have easily done it, but I just wanted to show you here on the screen instead of doing something, scribbling something on a notepad or something. So CH4 plus 2 times of oxygen. Well, here they've taken air, but I mean, you can disregard the nitrogen because it just comes out at the very end. So this is methane plus, so 1 mole of methane plus 2 moles of oxygen gives 1 mole of CO2 plus 2 moles of H2O. Now, if you look at the ratio of moles here for CH4 and oxygen, CH4 is the moles, or the ratio of the total mole fraction of CH4. Yeah, let me say that way. So the total total mole fraction of CH4 is 1 divided by 3, because the total number of moles are 3, 1 for CH4 and 2 for oxygen. So the mole fraction of CH4 is 1 divided by 3, and for oxygen it is 2 divided by 3, which is to say that the mole fraction of CH4 is 0.33, and for oxygen it is 0.66. Right, so that is exactly what we see here as well. And as always, I mean, you can actually look at it here also, and then you can do that same thing for mass fraction. So as we've just seen, by using this simple expression, we can set whatever equivalence ratio we want. We don't have to do all the calculations by hand. In fact, let's go ahead and change the equivalence ratio. Let's see what happens in that case. So instead of 1, which we had, let me put an equivalence ratio of 1.5. Hit enter, and now if I look at the mole fractions, see, now the mole fractions have changed. Now there is more fuel. It has become fuel rich, as we saw in the slide. So when the equivalence ratio is greater than 1, it becomes fuel rich, and the oxidizer has reduced, as you see, as compared to the previous state. If we go in the opposite direction, so instead of 1.5, let me see, 0.5, And now if we look at the mole fractions, now the fuel has reduced in terms of mole fractions. The oxidizer has increased. So now the mixture has become fuel lean. So this simple function is very, very useful. You will use it time and again. And it also has a relation with the excess air, but we'll do that at a later stage. But please remember this function. This is very, very important.